Alright, so I'm going to do the Solstice test. So this is for Lenexa, Kansas. It's at 121. The altitude is 74, so that's what I'm looking for. And so you can see Lenexa. And then I'll do in my drawing I have it set for Manhattan, so it's at 128, still at 74. Manhattan, so 124. Let's go ahead and see what I get with my apparatus here. So I'm looking for 165, 164. Alright. So I gotta get that so it doesn't get that shadow, so it's even. So I get 160. I don't know if you can see that or not. Get 164, 165 minus 90, which is 74. If I was at 165 minus 90 is 75. Looks like I'm at 164, 165. So that's when the Earth is tilted the most towards the sun. So I'm hand measuring this at 164, 165, 164. So how I know is when the shadow, you can see that shadow. So when you get that shadow directly where right there is how I know I'm right on. It's 164, 165. Yep, and then I'll do an AutoCAD drawing. of it to see if I match what I measured. So there will be a part 2. All right, so this is part 2. So I'm going to go ahead and begin with doing the calculation for the altitude of the sun. So I take 90, which already, well, I just cleared it out, 90 plus, or minus, excuse me, the latitude plus the tilt, which is 23.5 equals. So I'm looking, so I got yesterday, because today's 6/22, so 74.5, or 74. So Manhattan yesterday, it was 74, the altitude. Manhattan, Kansas, Manhattan. And this is for Lenexa, 74. But it's at 121. And Manhattan was at 128, so I chose 124. Kind of split the difference because my drawing's in for Manhattan, but it's not very far away from Kansas City. So alright, got that out of the way. So next I go into this NASA website and I got to get the measurement to the sun, center of the sun to the center of the earth on that day. So first I need to convert it from UTC time. Let's see here. So at 1:30, we're in daylight savings time. So at 1:30, or at 12:24, excuse me, 12:24. Or no, that was at 1:30. Excuse me. It was at 1:24. So I need to be at 1. So at 1, where is it? 1. So we got to subtract an hour. So at 1:24 is 19 minus that. So it's 18:24 is what I'm looking for. So 18:24. So I come over here to this NASA website, and I got this filled out. That's the sun, the target body, and this is the Earth. I got my times, and I skipped today, so I have a lot to work with, increments of 1 minute. And then I set up this table. This gives you the parameters to what you're working with, and I want it to be in kilometers. There's no other choices, really. So So then I say generate. Come down here to June 21st at 1824. So right there is the distance from center to center. So now I need to convert that because that's in kilometers. So kilometers to feet. And that's my distance. And we'll go into my drawing. So here's my drawing. It's in 3D. It's all to scale. So I draw a circle, and where they intersect is where I place it. So radius, and then paste that number, and then line int. So right there is where I got it. So then I'll go, and the reason why I know that is because if you look here, it's below. This is my ellipse, and it has a major and minor axis with the eccentricity. So is how you can tell is it's below the line there, and then you come up here and it's up above. So it's, somewhere there's an intersection in here. So right here is my intersection. So we'll copy. This is from back in 21, I guess, when I did it, because of the sun or the earth won't be always in the same place in each year. So we'll copy that to here, and then I strike a line from the center. We're gonna do that. Okay, so now I draw a line from the center of the earth. I could draw the sun here, but it's not necessary. To there. So I built this dome around it. This in the center of this is Manhattan. That's that's the east-west line. That's my north and south line with my arrow, and that's the axis. So right where that line hits is not seeing a problem here. Oh, I need to rotate it. So we can tell I need to get this line right here so it's rotated. So I gotta rotate it so it's 180 degrees to that line, because that's what I deleted it. See how it says 100 degrees south right here? So I gotta rotate it. Okay, so what I'm gonna do, rotate it more and then rotate it back, because I can't really tell which way to rotate it. So I get my Z from here to there from the axis, rotate. And then it just spins around along the axis. So we'll go right here, and then I'll redo it again, because I can clearly see that I need to go, this way. So rotate. Reference. And then let's do the equator and then line it to that line. Alright, now it should be 180. As you can see, that line, that's why I built this dome, is to help me guide without measuring. And it's at 180. Alright, so now I draw a line from my position in Manhattan to the center of the zone. I'm going to get 3 measurements here. One for the tilt, and one for the altitude, and then I'm going to get the one from Tropic Capricorn. So I think Manhattan's 15 degrees above it. So, which would be that line. So, first, let's measure. So I'm going to get the south and the center of me to the center of the earth. Center of the earth, and then measure that angle. Well, that's 15. No, I didn't do that one. Alright, hold on. Sometimes it gets a little tricky. So NEA here to, and then we'll go north there. Dimension. So I got 74.3 for the altitude of the sun. So, and that's what I got. 74.3. Actually, I have to write on according to this. So if you come over here, you see this 74, damn it. Let me get my computer fixed. I got 144 hertz, but it screams at me. I gotta lower it down to 100 or 60 hertz, and then it goes away. Alright. So wait, that's what that is. So I verified that that's correct. So now we'll get the tilt. So here, what was that? From here. I need to go from here, and NEA here. Dimension, angle. We just do it this way. From here to the center, back to here. That's what I was doing, missing. And then measure that. Nope, I know what I'm doing. So, yeah. So I need to come from that line here, NEA, from here to here. Angle. That's at 15. Alright, there's the tilt. Jeez. And it's 23.4. Trying to hurry. That's going from the equator to where the sun is. Anyways. So that's what I proved. And this line is a long ways. I think we're at 94 million miles. So the length. And so we'll go to feet to miles. So it's at 94. Gotta move that decimal place. Alright. I did want to add in two other things I kind of forgot to do it a different way. So we can also measure the tilt doing it this way as well. And then I'll get the difference between Tropic of Capricorn and my position. So we'll go 3 point. So we'll grab the tilt from here to the center to my location. Or actually to the line, that line. And then we'll go dimension, angle, grab the tilt. It's 113. Now a lot of people do say, it's 666, right? Well, if we change the units, so there's 2, and it'll become a 7. Or I thought it would have. 665. I thought it, for some reason, it was 667, not 666. So let's just undo that. So we take it from at 113, 4. Now minus that by 90. Alright, so 13.4 minus 90 equals 23.4.